A company is planning to manufacture computer desks. The fixed cost will be $60,000 and it will cost $200 to produce each desk. Each desk will be sold for $450. Write the cost function C of producing X desks.
What's our variable going to be?
Would it be 60,000 plus 200x?
No, just let's start with what our variable means. In other words, this tells me C of x means my variable is going to be x, but what is x?
Desks.
The number of desks, right?
Yeah.
Okay. So our cost function is what?
60,000 plus 200x.
Uh-huh. And then next it probably wants to know our revenue our revenue function and then our profit function.
Yeah. Or the break-even point.
Okay, well, the revenue function is what? This is our cost. This is our revenue.
200x minus 450.
That's part of the cost. Our revenue is only a function of that thing right there, what we sell each desk for.
Okay.
So the revenue function would be 450x. Okay. Now, did they ask about profit function also?
Break-even point.
Break-even point. Okay. Well, the break-even point is where the cost function equals the revenue function. That would be a zero profit, but that's okay. We can solve that. Our cost function is our revenue function is that. That's one equation, one variable. You get 250x equals 60,000. So what does x equal to? 250x equals 60,000. Do you have a calculator?
Yeah. $240?
140?
240.
240, okay. Sounds closer. Yeah. So, if they make and sell 240 desks, they will break even. If they make more, or actually if they sell more, you don't want to make more and sell less. So your break-even function is kind of based on selling every one that you make. But if they were to sell more than 240 desks, they would have a profit. If they sell less than 240 desks, they would actually be at a loss. Any other questions on this particular problem?
No.
Okay.
A paper manufacturing company converts wood pulp to writing paper and newsprint. The profit on a unit writing paper is $500, and the profit on a unit of newsprint is $350.
$350?
Yeah.
Okay.
What X represent the number of units of writing paper produced daily? Let Y represent the number of units of newsprint produced daily. Write the objective function that models total daily profit.
I find it extremely helpful to spell out the meaning of your variable exactly, because it isn't always clear with some of these harder problems. In other words, this is the number of units of... What kind of paper is this first one, X?
Writing paper.
And the second one is newspaper?
Newsprint.
Newsprint, okay. All right, and what's this 500 again? That's the
profit on writing paper.
Okay, so that's profit on each unit of writing paper?
Yeah.
And this is the profit on each unit of newsprint. So what's our, and what do they want to know?
So it says the manufacturer is bound by the following constraints. Equipment in the factory allows for making at most 200 units of paper, writing paper, and newsprint in a day. Regular customers require at least 10 units of writing paper and at least 80 units of newsprint daily.
Okay, so X plus Y has to be less than 200?
Yeah.
Which one's less than 10? What were the other constraints?
X is less than 10. Oh, greater than or equal to 10.
And the other one was 80? Had to be greater than or equal to 80?
Yeah.
Are those three constraints correct?
I think so.
Okay. And the question is, write the objective function for the profit?
Yeah.
Okay. Well, what is our profit function? As a function of X and Y,
10x plus 80y.
no, what is our profit function? What do we make as a profit? If we...
Oh, 500x plus 350.
Yeah, that is our profit function. That's the thing we want to maximize when we get around to dealing with these other constraints. Now, each of these constraints can be graphed as a linear relationship. What's their question again?
Write the objective function that models total daily profit.
Are we done? Yeah, we are. We've answered that question. They're going to ask a second part, though, and that is maximize that function.
Mm-hmm.
Right?
Yeah.
Okay. Here's our profit function. Now, if we want to know what value of X and what value of Y will maximize our profit, which everybody wants to do, maximize their profit, well, we have to take this linear programming approach. And the way you do it is you graph your constraints and you check the vertexes of the resultant area that you get. And whichever vertex produces the greatest profit, that is your answer. All right, so let's graph this line here. How do I do that?
Y is 20 and X is 200. I mean, they're both 200.
Yeah, if I want to graph that relationship as an inequality, how do I do it?
So there's the y-intercept is 200.
Okay.
And the x-intercept is also 200.
The slope is what?
1.
Minus 1. We've got to take the x to the other side. So it makes it minus 1. So if I make this point here 200, and I draw a slope of minus 1, that's that line. Now, the only thing I made a mistake of is I didn't make it dotted. Here, let me make it dotted. And you see why it has to be dotted?
Yeah, because it's less than,
Right.
instead of less than or greater.
Right. Now, let's look at our other two constraints. X has to be greater than or equal to 10. Well, on my graph here, that's like right here, 10. Okay? So, this solid line. So far, we're in this area here, right? Our solution has to come from that area. But we've got one more constraint, and that's y has to be greater than or equal to 80. Well, if I put 80 on here, it's about right there. That's a solid line. Now, this area here is where my solution set has to come from. And what I need to do is to plug in this value for x and y into my profit function, get a number. Plug in this value for x and y into my profit function, get a number. This value, and compare all three numbers. Whichever one's the biggest, that's the maximum profit you can make given these constraints. So that's the concept. Now, we have to know what those points are. What is this point here?
Something 80.
Okay. How do we figure out what the something is?
Very equal.
Let's go up and look at this function right here. X plus y is less than 200. Well, that's on that line. So if y is 80, x must be 120. So the coordinates of that vertex are this, 120, 80. That's going to be one of the points we plug into our profit function. But let's examine this vertex. What is that vertex?
10, 190.
And finally, I'm not sure I've ever seen one where this results in the maximum, but that number is clearly 10, 80. Okay? So, what we know is that our maximum profit comes from one of those vertexes. It doesn't come from a point on this line. There's no way that point produces the maximum profit. That's what we know from linear programming, is that our maximum profit comes from one of those vertex points. Okay, now I'm going to erase this over here, and we're going to test each point and figure out what the profit is. So let's take the top point. What is the profit of 10, 190?
So 500 times 10.
5,000.
So 5,000.
Put the other.
Plus.
What's the other one?
63,000.
I'm sorry, I didn't hear you.
63,000.
63,000?
Yeah.
Okay, so that total is 68,000.
Wait, actually it's 66,500.
I'm sorry. 66?
Yeah, like the total is 60. It's 5,000 plus 66,500.
So what's the total profit after you add them together?
71,500.
71,500. Okay, I made a mistake in one of these, but I won't worry about it at the moment. So all we need is a bottom line number. So let's examine this set of numbers. I got to think this is going to, yeah, this got to be much better. 60,000 right off the get-go, is it not?
Yeah.
Plus, what's 350 times 80?
28,000.
Okay. So regardless if my math is right or wrong on the first one, that's not the maximum. This is. And just to see what happens if we plug in this usually produces a minimum. And notice that it absolutely has to, we don't even need to do this one because it has to be less than that one. I'm substituting 80 for y and I'm substituting 16 instead of 120, so there's no way this is going to be the maximum. I don't even need to test it. It would be a much smaller number. That is linear programming. I'm impressed that you're getting this towards the end of, well, you're on a trimester, but usually what I have found is that Algebra 2 students get this at the very beginning, and this is like the hardest part of Algebra 2. It's terrible to teach this at the beginning of the course. It demoralizes everybody. Not that it's that hard, but it's different. It's more difficult. These are some of the more difficult word problems for sure.
Yeah, these confuse me now.
Yeah, they are definitely harder. You got this thing called an objective function, and then you got all these other things that are the constraints on the objective function.
Well, the other ones are like, you have to see graphs.
Okay. You can take a picture of it and send it to my email real quick. It'll take about a minute. Or just remember in the future that if you're going to be dealing with problems where I have to see graphs, you need to do that. And maybe do it in advance of our session. It just depends on whether you want to. You can probably, are you familiar with using your camera to take a picture and send it to an email?
Yeah, I found another one.
Okay.
Two adjoining square fields with an area of 2,900 square feet are to be enclosed with 200 feet of fencing. The situation, find the length of each side where variables.
All right, I didn't quite hear. We have two adjoining squares?
Yeah.
And they have a combined area of 2,900 square feet?
Yeah.
And we have 200 feet of perimeter fencing?
240 feet.
240 feet of fencing material.
Yeah.
And we have to figure out the dimensions. Okay? Tell me where to start.
Would it be like y plus x equals?
Well, you got to always define your variables. That's any word problem that you encounter. It will be made so much easier if you start out by defining your variables. So, what should I make x? What should I make y? Or give me two variables you want to use.
The small square would be y.
The small square, the side of the small square?
Yeah.
Okay.
And then the other one should be x.
Okay. Now, notice that x can be any relationship we want to y as long as it's greater than y. In other words, it could be a much bigger square than I've drawn here. Okay. So, what's the area equal to of these two squares? What's the area of the little square?
Y times y.
What's the area of the big square?
X squared.
And we're told that that is 2,900. Now we have 240 foot perimeter. The perimeter, well, what's the equation of the perimeter? This is x, that's y, that's y, that's y. And this is x.
4y plus 4x.
How many y's?
4.
We don't need fencing for this part here.
3y plus 4x.
Well, we don't need fencing for this part here. So it's 3y. Let's check it off. Let's go through each part here and put a hash mark through it. So 3y takes care of that part of the fence. Plus 3x takes care of this 3 parts of the fence. What takes care of that part right there?
B.
No, don't introduce a third variable because we only have 2 equations. If we can stick with these 2 equations in x and y, we can solve this thing for both x and y. If you have 2 equations and 2 variables, you can solve it. What's this distance right here in terms of x and y?
Y minus x.
Well, x minus y. It's the bigger minus the little. Right? In other words, the big one is x, the little one is y, so this distance right here is x minus y. And that completes our perimeter. So now we need to solve this system of simultaneous equations. Well, let's simplify the second one. First one is y squared plus x squared. Let's put it in standard format. Standard format has the x squared first, just to keep things consistent. What's that simplified to?
Isn't that just the same?
No. That's 4x. That's 2y. And what's that equal to? 240. So there's our 2 equations and 2 unknowns. Now, where is our solution going to come? Well, let's graph this. What's this equation the equation of?
A circle.
With a radius of the square root of 2,900. What's this an equation of?
A line.
With a negative slope going through an x-intercept of 120. Now, let's see. Is the square root of 2,900 greater or less than 120?
Greater.
Okay, so that line must do that. something like that. Right? Where is our solution for x and y? It's not here, because that would result in a negative x.
That little triangle.
This right here would result in a negative y, so I must not have drawn it correctly. I mean, I just drew it. I didn't draw it accurately. I just estimated it. But it probably looks something more like that. And now we have a solution that has a positive x and a positive y. So, let's solve it algebraically. How do I solve this algebraically? In other words, how do I come up with those numbers?
Couldn't you just make x squared 0 and then take the square root of 2900 to get x?
The one way I can do it for sure, I'm sitting here thinking about how can we do this with elimination? Well, not so easily we can't. In other words, I can't figure out how to eliminate a variable, but I could certainly do it with substitution, right? I can solve the second equation for y easy enough and substitute it for the y squared of the first equation. I'll have an equation all in x, and I can solve it. It'll be a quadratic. It'll give me two solutions. I'm going to throw away that solution and take that solution. So let's do that. Y is equal to minus 2x plus 120, correct? From the second equation. So now I'm going to go in and substitute that wherever I see y on the first equation. They don't give you easy problems, I will say that. Now maybe they meant for you to solve this on the calculator. Is that possible? Or you think you were supposed to solve it manually?
Yeah.
Okay. Notice that what we're going to end up with here, it's a quadratic in x. Okay? X squared plus 4x squared minus 24480x plus 14,400 equals 2,900. I think I expanded that properly. Did I?
Yeah.
Okay. Now let's bring this 2,900 to the left and combine everything. Well, we got 5x squared minus 480x plus, what's that minus 2,900, 11,500 equals 0, 11,500. Can divide everything by 5. Notice that a number is divisible by 5 if its last two digits. Well, actually, if it ends in 0 or 5. So I know I can take a 5 out of everything. And I don't know if that's going to help us much. It's still going to be difficult to factor. Factors of 2,300 that subtract to 96? I don't think so. Well, maybe. Maybe. No, they have to add to 96. Well, that ain't going to happen. 15 times 15? No, that's not even close. 80 times 10? Not even close. This seems to me that it has to be imaginary solutions. Will you hold on 1 second, please? 1 moment, Mina. I'll be right back.
All right.
Well, possible I've made a math error here, although I don't see where it's at. But what's 96 squared?
$9,216.
Okay. So 9,216 minus 4AC, which is 9,200. That's 4. That gives you a discriminant of 4. So my answer is 96 plus or minus 2, all divided by 2. So my two factors must be 49 and 47. What do 49 and 47 multiply to be? 2,300, right? No.
We all.
Huh?
We all.
Wow, how did that happen? 4AC was 9,200. Subtracted from 9,216 gave me 16. Square root of that was 4, not 2. This was 4. So my answer is 96 plus 2 and 48 plus 2 and 48 minus 2. There's your two factors right there, 50 and 46. X minus 50, x minus 46. So there's your two solutions. X could be 50 or x could be 46. Yeah, both of those solutions might work. Now, we still haven't solved for y. I realize we're out of time here. We can solve for y by taking our x solutions and going in and putting it in for y. If both of those solutions create a positive y, then you have two solutions to this problem, two different configurations that would work. If one of them produces a negative y, in other words, if I take this 50 solution, no, that produces a positive y. So does the 46. So it looks to me like there's two possible configurations. One would be an x of 50, the other would be an x of 46, and each one of those would have a y coordinate also, which means my drawing must have been more like this. Where I have two solutions, and they both have positive x's and positive y's. Good to go, Mina? Bringing me those challenging problems. These are good. These are really good. Well, I will talk to you next time, whenever that is. I might see you before the next year, the way you work. Okay?
All right,
All right.
thank you.
Good night. Bye-bye.